tonight, we're going to explore something that no one warned you about when you were learning about the cosmos. Not the death of the sun, not the heat death of the universe, not the evaporation of black holes or the decay of the last proton. Those things are true and they are coming, but they are not the most profound thing physics has to say about the ultimate fate of everything. The most profound thing is this: the universe will forget. Not in a poetic sense, not as a metaphor for the way civilizations crumble and names are lost and languages die. In a precise, physical, thermodynamic, information theoretic sense, the universe will eventually reach a state in which every record of everything that has ever happened, every trace of every event in 13.8 billion years of cosmic history is completely, irreversibly, permanently gone. The supernova that created the atoms in your body, the first star that ever ignited, the first galaxy that ever formed, the first moment that anything as complex as a living cell ever existed anywhere in the universe. The thoughts you are having right now, every book ever written, every conversation ever spoken, every measurement ever recorded, every piece of information ever encoded in any physical medium anywhere in the observable universe. Gone. Not just inaccessible, not just scrambled, not just encoded in a form we cannot read. Gone in the absolute sense that the laws of thermodynamics allow, erased from the physical record of the cosmos as completely as if it had never occurred. This is not speculation. It follows from the laws of physics with the same certainty as the prediction that the sun will eventually exhaust its hydrogen fuel. The question is not whether the universe will forget. The question is exactly how it happens, on what timescale, through what mechanism, and what that total cosmic forgetting means for the question of whether anything we do matters. And here is the extraordinary thing. When you follow the physics carefully, when you trace the mechanism of forgetting through thermodynamics and information theory and quantum mechanics and cosmology, you discover that the universe's ultimate forgetting is not a tragedy. It is something far more interesting than that. It is the other side of a coin whose first side is the fact that we exist at all. 7 things physics tells us about how and why the universe will eventually forget everything, each one more surprising than the last. Before we begin, if these questions about the ultimate fate of information, of memory, of everything that has ever happened, are the kind of questions that stay with you, hit like or subscribe. It costs nothing and helps us reach more minds that want to think about things like this. Now let's begin. The year is 1867. A Scottish physicist named James Clerk Maxwell, the same Maxwell who derived the equations governing electromagnetism, who predicted the existence of electromagnetic waves 20 years before Hertz confirmed them experimentally, is thinking about the relationship between thermodynamics and information. Specifically, he is thinking about whether the second law of thermodynamics, the law that says entropy always increases in a closed system, could ever be violated. He imagines a thought experiment. A small container divided into 2 chambers. In one chamber, warm gas with fast-moving molecules. In the other, cool gas with slow-moving molecule. The 2 chambers are separated by a wall with a tiny door. Standing at the door is a tiny hypothetical being, later named Maxwell's demon by Lord Kelvin, who can observe the molecules approaching the door and choose to open or close it selectively. Fast molecules from the cool side are let through to the warm side. Slow molecules from the warm side are let through to the cool side. Over time, the demon's selective operation of the door concentrates the fast molecules in one chamber and the slow ones in the other. Temperature difference increases. Order increases. Entropy decreases. The second law appears to be violated. Maxwell knew something was wrong with this picture. The second law had been established by Carnot and Clausius and dozens of experimental confirmations. It was not wrong, but he could not pinpoint the flaw. For 60 years, the demon resisted resolution. Then in 1929, the Hungarian-American physicist Leo Szilard showed that the demon's act of measuring which molecules were fast and which were slow had to be taken into account. Measurement has a physical cost. The demon must record information about each molecule, and maintaining that record eventually requires erasing information, which generates entropy. The entropy generated by erasing the demon's memory is exactly sufficient to compensate for the entropy reduction it produced in the gas. The resolution was completed in 1961 by Rolf Landauer at IBM. Landauer proved what is now called Landauer's principle. Erasing one bit of information in a physical system must release a minimum amount of heat, equal to the temperature of the system times Boltzmann's constant times the natural logarithm of 2. The act of forgetting, the physical erasure of stored information, is thermodynamically irreversible and generates entropy. Landauer's principle is the bridge between information theory and thermodynamics. It says that information is not abstract. Information is physical. It is stored in physical systems. Its erasure has physical consequences, and those consequences include the generation of heat, the production of entropy, the irreversible loss of physical order. The universe will forget everything for the same reason. It cannot violate the second law of thermodynamics, because remembering requires physical storage, and every physical storage medium eventually degrades, and degradation means information loss, and the universe's total physical substrate for storing information is running out of the thermodynamic gradient needed to maintain any storage at all. This is the story of how physics erases its own record. The first discovery. Information is physical, and the universe has a finite capacity to store it. Information is not abstract. This statement sounds trivial, but its implications are profound. Every piece of information that exists, every bit of data, every record of any event, is stored in the physical state of some material system. The memory in your brain is stored in the pattern of synaptic connections between neurons. The information on a hard drive is stored in the magnetic orientation of tiny regions on a spinning disk or the charged state of transistors. The information in a book is stored in the arrangement of ink molecules on paper. The information about the early universe preserved in the cosmic microwave background is stored in the polarization pattern and temperature distribution of photons filling the entire observable cosmos. In every case, information is a physical configuration of a physical system. It requires matter or energy arranged in a specific pattern, and it requires that pattern to be distinguishable from other possible patterns. A single bit of information requires a physical system with at least two distinguishable states, which we call 0 and 1. The universe's total capacity to store information is therefore limited by the total number of distinguishable physical states that exist within it. This number is finite, though enormous. The maximum information content of any region of space is bounded by what is called the Bekenstein bound, derived by the physicist Jacob Bekenstein in 1972. The maximum information that can be stored within a spherical region is proportional to the area of the region's boundary in Planck units, not its volume. This is a surprising result, and it is deeply connected to the physics of black holes. The observable universe contains approximately 10 to the 80 atoms of ordinary matter. Each atom has multiple degrees of freedom, each capable of storing information. The total information capacity of the observable universe is estimated at roughly 10 to the 120 bits, a number so enormous it makes a Google look small. small, but it is finite. The universe has a finite information storage capacity, and as the universe evolves toward the heat death, as matter decays and concentrates into black holes, and those black holes evaporate, the available physical substrate for storing information decreases. The capacity to remember shrinks. This matters because every record, every trace of every event requires information storage. The arrangement of atoms in a fossil encodes information about the organism that left it. The light spectrum from a distant galaxy encodes information about its composition and age. The gravitational wave signal from a black hole merger encodes information about the masses and spins of the colliding objects. All of this information is stored in the physical state of the universe. As the universe forgets, these physical records degrade. The fossil is dissolved by chemistry. The galaxy's photons are redshifted to negligible energy, and their information content dispersed into the background radiation. The gravitational wave signal is diluted across an expanding universe until it is indistinguishable from the noise. Information is not lost in the sense of violating any conservation law. In quantum mechanics, information is conserved in principle. The total information content of a closed quantum system never changes, only its distribution among degrees of freedom. But information can become thermodynamically inaccessible. It can be scrambled so thoroughly, dispersed so uniformly, encoded in correlations between so many degrees of freedom that extracting it would require more resources than the universe contains. When information becomes thermodynamically inaccessible, it is, for all practical and physical purposes, forgotten. The distinction between information being destroyed and information being irreversibly scrambled is philosophically interesting but physically irrelevant. In either case, the record is gone. The universe has forgotten. The second discovery: every medium for memory has an expiration date. The universe stores information in many forms. Each of those forms has a physical lifetime, a maximum duration over which the information can be preserved. Consider the most durable storage medium available to biology: rock. Stone tablets, the physical carving of information into hard crystalline mineral, protected from erosion by burial or aridity. The oldest human writing, cuneiform on clay tablets from ancient Mesopotamia, is about 5,000 years old. Some Egyptian hieroglyphics inscribed in granite have survived for more than 4,000 years. The physical durability of stone as an information storage medium is impressive by human standards. By geological standards, it is negligible. Rock is subject to subduction, to the slow movement of tectonic plates that carries rock into the mantle, where it is melted and chemically reconstituted over time scales of millions to hundreds of millions of years. The rock that preserves ancient writing will eventually be destroyed by the geological processes of a living planet. Earth's tectonic activity has a geological memory of perhaps 1 billion years at most, beyond which rocks are typically recycled. What about chemical information storage? DNA, the molecule that encodes the genetic information of living organisms, is extraordinarily sophisticated. The double helix structure, the complementary base pairing that allows information to be read and copied with high fidelity, the repair mechanisms that correct copying errors, all of these give DNA a remarkable longevity compared to other biological information storage systems. The oldest recovered ancient DNA from permafrost-preserved samples is roughly 1 million years old. The information content is degraded but partially readable. But DNA is chemically reactive. It is attacked by water, by oxygen, by cosmic rays, by heat. In the absence of protective mechanisms, without the cellular machinery that actively repairs and copies DNA, the molecule degrades on time scales of thousands to millions of years. A DNA molecule sitting in the open without protection will have its information completely destroyed by chemical degradation in a cosmologically trivial span of time. What about more exotic information storage? The universe itself has stored information about the Big Bang in the cosmic microwave background. The pattern of temperature fluctuations in the CMB encodes information about the quantum state of the universe at 380,000 years after the Big Bang, information that has traveled for 13.8 billion years without being completely destroyed. But this information is encoded in photons, and photons are subject to redshift, to scattering, to the eventual heat death of the universe that will stretch them to negligible energy. The information in the CMB photons is not permanently preserved. It is slowly scrambling as the photons interact with the matter they pass through, as their wavelengths extend with cosmic expansion, as the universe's thermal evolution dilutes and disperses their information content into the vast equilibrating sea of increasing entropy. Every medium has an expiration date. Biological memory decays in years to decades without active maintenance. Written records decay in thousands to millions of years, depending on material and environment. Geological records decay in millions to hundreds of millions of years through tectonic recycling. Stellar records, the elemental abundances in stellar atmospheres that carry the chemical signature of previous stellar generations, persist for billions of years before the star's death destroys them. Even the largest scale cosmological records, the distribution of galaxies that encodes the history of structure formation, will eventually be erased as the accelerating expansion of the universe separates galaxy clusters and removes information about their mutual history beyond the cosmic horizon. The universe has no permanent storage medium. Every way that information is preserved is temporary. Every record has an expiration date. Given sufficient time, every expiration date arrives. The third discovery, the accelerating expansion, is the universe actively erasing its own history. Here is something that should fundamentally change how you think about the accelerating expansion of the universe. The discovery that cosmic expansion is accelerating, confirmed in 1998 by the supernova observations that won Perlmutter, Schmidt, and Rees the Nobel Prize, is usually presented as a discovery about the future fate of the universe. In the far future, galaxies will recede beyond our cosmic horizon. The observable universe will shrink. We will be left with only the local group as our observable cosmos. But the accelerating expansion is not just a statement about the future, it is also a statement about the past. And the statement it makes about the past is extraordinary. Every galaxy that has already crossed our cosmic event horizon, every galaxy whose light will never reach us again because it is receding faster than light, has taken its information with it beyond our reach. The events that occurred in those galaxies, the stars that formed and died there, the planets that may have formed, the civilizations that may have risen and fallen, the gravitational waves from their mergers, the light from their supernovas, all of it is gone from our observable universe as effectively as if it had never happened. This is not just a practical limitation. It is not like saying that we cannot currently receive the signals because our technology is inadequate. The signals will never arrive. Not because of any obstacle, because the expansion of space between us and those regions has outpaced the speed at which light or any other signal can traverse that space. The information about those events is permanently beyond any possible receiver in our observable universe. The accelerating expansion is the universe deleting information from its observable record at an increasing rate. With each passing eon, more regions cross the horizon. more information becomes permanently inaccessible. The cosmic event horizon is the universe's own deletion mechanism, eliminating records faster and faster as dark energy drives the expansion to ever greater rates. In the far future, the acceleration continues. Galaxy clusters that are now within our observable universe will eventually cross the horizon. Individual galaxies within our local group will remain gravitationally bound against the expansion, but they will become increasingly isolated in an otherwise empty, observable cosmos. The information about the rest of the universe, the 100 billion other galaxies we can currently observe, will be locked behind a horizon we can never cross. From the perspective of observers in the far future, the universe will appear to contain only the few gravitationally bound structures in their immediate vicinity. The evidence for the Big Bang will still be present in the fading microwave background. The evidence for the universe's age will still be encoded in the composition of old stars. But the vast panorama of cosmic structure that we can observe today, the web of filaments and voids and galaxy clusters spanning billions of light years, will be gone from any possible observation. The far future universe will not just be smaller in practice, it will be fundamentally impoverished in information. The records that allowed our era's cosmologists to reconstruct the history of the cosmos will have been deleted by the expansion itself. The universe in the far future will not be able to determine how large the total universe is, whether there are other galaxy clusters beyond the horizon, what the large-scale structure of the cosmos looked like during the era of peak star formation. The accelerating expansion is the universe progressively forgetting its own history. Each passing eon is another entry deleted from the cosmic record. The fourth discovery: black holes. Both remember and destroy. Black holes have a paradoxical relationship with information. They are, on one hand, extraordinarily good at preserving information. On the other hand, they may be the universe's most efficient information destroyers. Understanding which one they are is one of the deepest unsolved problems in fundamental physics. When matter falls into a black hole, every property of that matter, its mass, its charge, its angular momentum, contributes to the properties of the black hole. But the specific details, whether the matter was arranged as a star, or a gas cloud, or a library, or a civilization, appear to be lost. Black holes have no hair, as the physicists say. The no-hair theorem states that a black hole is fully characterized by just three numbers: its mass, its charge, and its angular momentum. All other information about what formed the black hole is gone from the exterior of the event horizon. This is the black hole information paradox. When matter falls in, the information about its specific configuration disappears. If the black hole then evaporates through Hawking radiation, and the Hawking radiation is purely thermal and contains no information about what fell in, then the information is genuinely destroyed. The quantum mechanical evolution of the universe has produced an irreversible loss of information, violating the unitarity of quantum mechanics, one of its most fundamental principles. Most physicists believe information is not actually destroyed. They believe Hawking radiation is not purely thermal, that it encodes the information about what fell in through subtle quantum correlations in the emitted photons. The information comes out, but it is scrambled almost beyond any conceivable recovery. The black hole is not an information destroyer. It is an information scrambler of extraordinary efficiency. Stephen Hawking conceded this point in 2004, acknowledging that the information was preserved in principle in the Hawking radiation after a bet with John Preskill and Kip Thorne. He remained less certain about the mechanism by which the information was preserved. But here is the critical point for the universe's ultimate forgetting: whether information is truly destroyed or merely scrambled by black holes. The effect on the universe's ability to access that information is the same. A black hole that has swallowed a library and then evaporated has released the information in the library in the form of Hawking radiation. But that radiation is emitted at a temperature inversely proportional to the black hole's mass. For a supermassive black hole, the Hawking temperature is extraordinarily low, far colder than the current cosmic microwave background. The radiation is emitted as an incredibly faint, long wavelength stream of photons and particles over time scales of 10 to the 100 years or more. By the time the last black hole evaporates, the Hawking radiation from it has been emitted into a universe that has itself expanded enormously. The photons from the radiation are redshifted to extraordinary low energies. They are dispersed across a volume so vast that the information they carry, encoded in their quantum correlations, is spread over a region so large that no physical system within the universe could ever gather enough of them to reconstruct the original information. The information is preserved in principle, but it is thermodynamically inaccessible in practice. The distinction between in principle and in practice is exactly the distinction between physical forgetting and philosophical forgetting. The universe physically forgets. Philosophical forgetting, the question of whether the information exists in some abstract mathematical sense, even if no physical system can access it, is a different question that physics alone cannot answer. What we can say with confidence is this: after the last black hole evaporates, no physical system anywhere in the universe possesses enough energy or physical resources to reconstruct from the Hawking radiation the information about what the black hole originally consumed. The information about the black hole's formation, and through the black hole's formation, the information about everything that went into it, is physically inaccessible. The universe has forgotten, not because the information was destroyed, because the information was distributed so uniformly across such vast volumes at such low energy that no conceivable physical process could ever gather enough of it to reconstruct anything. This is maximum entropy. This is thermodynamic equilibrium. This is what the universe's forgetting looks like at its completion, the sixth discovery. Consciousness is the universe's most fragile archive. Of all the information storage systems that the universe has produced, consciousness is simultaneously the most extraordinary and the most ephemeral. A human mind at any given moment contains approximately 100 trillion synaptic connections, each contributing to the information that constitutes a person's memory, knowledge, experience, and sense of self. The information content of a single human brain is estimated at around 2.5 petabytes, roughly 2 million gigabytes, stored in the pattern of neural connections, neurotransmitter concentrations, epigenetic modifications, and electrochemical states of the 100 billion neurons in a human brain. That information is the most complex and most fragile record in the known universe. It is the record of a lifetime of experience, a continuous archive of sensory input and emotional response and intellectual engagement and social relationship. It is the record of the person, the most precise and comprehensive account of what it was like to be alive at a specific place and time in cosmic history. And it survives for 70 to 80 years on average before being completely erased. The death of a person is the most dramatic routine information erasure event that the universe performs. Everything that person knew, everything they experienced, the specific texture of their consciousness, their particular perspective on the world, is erased on a timescale of decades. Not gradually lost the way a book degrades over centuries. Erased suddenly, completely, when the neural architecture that instantiated it ceases to function. Some of what a mind contains is transmitted to the world before its erasure. Books, art, music, spoken words, the cultural transmission of ideas and values extend the effective lifetime of some information beyond the death of the individual who originally encoded it. But this transmission is always partial and always lossy. The feeling of reading a specific passage for the first time, the specific quality of a remembered conversation, the ineffable character of a person's perspective on the world, these cannot be transmitted. They exist only in the original neural architecture and are lost with it. Over centuries and millennia, even the transmitted fragments erode. Languages die. Books are lost. Cultural contexts shift so dramatically that transmitted ideas lose their original meaning. The information that survives transmission degrades in fidelity with each transmission, like a photocopy of a photocopy, until eventually the specific content bears only a tenuous relationship to the original. Civilizations are archives with expiration dates. Everything a civilization knows, everything it has discovered and recorded and transmitted, exists in a physical substrate that is subject to the same thermodynamic fate as everything else. The physical media can be preserved against natural degradation through active maintenance. Libraries can be fireproofed. Digital archives can be backed up. Languages can be taught. But active maintenance requires a functioning civilization, and civilizations are themselves physical systems subject to entropy. On the time scale of the Earth's geological history, every human civilization is a momentary flash. The Earth will be absorbed by the expanding sun in approximately 5 billion years. Every physical record of every human civilization will be destroyed by that event. Every book, every hard drive, every monument, every fossil, every gravitational wave we have ever produced will be consumed by the sun's expansion. Nothing of human civilization as a physical record will survive the sun's death. Not because human civilization is insignificant, but because every physical record requires a physical medium, and every physical medium in the Earth's vicinity will be destroyed by the expanding sun. What about records we might place off Earth? The Voyager spacecraft, as we have explored in previous videos, carry golden records with sounds and images from Earth. They will survive the sun's death. They will be drifting through interstellar space when the sun becomes a red giant. They will survive the sun becoming a white dwarf. They carry the faintest possible physical trace of human civilization into the deep future. But over cosmic time scales, even Voyager's golden records are temporary. If proton decay occurs, The atoms of the golden records will eventually decay. The information they carry will be lost. Not in billions of years, in 10 to the 34th years, when the last proton decays and the last fragment of the golden record dissolves into radiation and leptons. On that timescale, humanity has been forgotten by the universe. Completely, irreversibly, as thoroughly as if we had never existed. Let's step back from this timeline for a moment, because there is something important to say about what we mean when we say the universe forgets. And there is something important to say about what the universe is forgetting tells us about the value of what happens before the forgetting. The Voyager Golden Record was made by people who knew they were mortal. Carl Sagan, who championed the record's creation, knew that no individual human life was permanent. He knew that civilizations rise and fall. He knew that even the Earth itself was temporary. He wrote about the pale blue dot with full awareness that the pale blue dot would eventually be absorbed by the sun, that the sun would eventually become a white dwarf, that eventually even white dwarfs cool and fade. And yet he made the record. And yet the team at NASA devoted enormous care and thought and creativity to its contents. They chose music from around the world with the deliberateness of people who believed that what they were choosing mattered. They selected images of Earth with the attention of people who believed that what the images showed was worth showing. They addressed greetings to possible future civilizations with the sincerity of people who believed that the act of greeting was meaningful, even if the greeting was never received. Why? Not because they were deceiving themselves about the permanence of what they made. Sagan, in particular, was too clear-eyed about the physics of cosmic time to believe in any naive permanence. He made the record because the value of an act is not solely determined by how long its effects persist. The record was worth making because the making of it was an expression of what human beings are. Because the reaching out, the attempt to communicate across distance and time and possibly species, was itself meaningful regardless of whether communication was ever achieved. This is the answer to the question that the universe's forgetting raises about meaning. The universe's forgetting does not retroactively subtract value from what happened before the forgetting. The forgetting is future. The value is present. The fifth discovery. Even the laws of physics leave no permanent record in matter. Here is a question that sounds strange but turns out to be physically meaningful. What evidence will remain in the far future of the universe that any of the events of cosmic history actually occurred? In the era of peak star formation, around 10 billion years ago, the universe was producing hundreds of solar masses of new stars per year in large galaxies, hundreds of times the current rate of star formation in the Milky Way. The cosmic noon. Stars were igniting everywhere, burning brightly, exploding as supernovas, enriching the interstellar medium with heavy elements, seeding the next generation of stars with the chemical complexity needed for planets and potentially for life. That era is over. It happened. The stars of that era lived and died. Their light crossed the universe. Their supernovas scattered their elements. The evidence is still here. We can detect it. The heavy element abundances in old stars that formed from supernova-enriched gas carry the chemical signature of those ancient deaths. The light from distant galaxies still arriving after billions of years of travel, shows us those galaxies as they were during peak activity. But on what time scale does this evidence survive? The old stars that bear the chemical signatures of early stellar generations will last, in some cases, trillions of years. Red dwarfs formed from the first enriched gas are still alive and will be alive for 100 trillion years. But when they die, their information is dispersed. The chemical abundances in their envelopes are scattered into the interstellar medium, diluted and mixed with material from other sources. The specific record this star formed from gas enriched by supernovas that occurred 12 billion years ago is gradually scrambled into the uniform background composition of the interstellar medium. Beyond the stellar era, when all stars are dead and the universe contains only stellar remnants, white dwarfs and neutron stars and black holes, the physical records are more durable in some ways and less durable in others. A white dwarf persists as a cooling ember for trillions of years, its composition encoding the history of its parent star. But white dwarfs cool toward invisibility. Their information about stellar composition is preserved in the arrangement of their atoms, but those atoms are gradually losing the thermal energy that would allow any external system to read that information. A cold black dwarf, the theorized end state of a white dwarf that has cooled for long enough, is an information repository with no accessible way to extract the stored information from outside, and then proton decay occurs. If protons are unstable, as most extensions of the Standard Model predict, then over timescales of 10 to the 34th years or so, every proton in every white dwarf decays. The white dwarfs dissolve. The atoms of which they are composed no longer exist. The information encoded in the specific arrangement of those atoms is destroyed along with the atoms themselves, not scrambled, not dispersed. The physical medium carrying the information undergoes a fundamental transformation that does not preserve the information in any accessible form. After proton decay, the universe contains no ordinary matter. The information records that ordinary matter carried are gone. Not just inaccessible, gone along with the medium that stored them. What remains are black holes, electrons, positrons, photons, and neutrinos. The black holes carry within their mass and spin and charge some information about what fell into them, though scrambled. The Hawking radiation they slowly emit carries that information in an increasingly inaccessible form as it disperses. The electrons and positrons eventually encounter each other and annihilate to photons. The photons redshift to ever lower energies as the universe expands. Each step of this process is a step in the universe's forgetting. Each transition from one form of matter to another is a loss of the detailed information that the previous form carried. By the time the last black hole evaporates and the universe is nothing but a dilute sea of low-energy photons and neutrinos expanding through an exponentially growing void, every physical record of every event in cosmic history has been erased. The universe has no memory. It does not remember the Big Bang because every physical record of the Big Bang's specific initial conditions has been scrambled. It does not remember the first star because every atom that star produced has either fallen into a black hole and been evaporated or decayed through proton decay. It does not remember us. It does not remember anything. The universe is not just forgetting its history, it is forgetting its laws. not in the sense that the laws themselves change. The laws of physics, in our current understanding, do not change over cosmic time. But the information about how those laws operated, the specific solutions to the equations for every specific physical system that has ever existed, is being erased. The laws will remain. Their application to specific systems, the record of what actually happened under those laws, will be gone. What does the universe's ultimate forgetting mean for the question of whether anything matters? This is the question that the physics raises most urgently for anyone who sits with it. If the universe will eventually forget everything, if every trace of every event in cosmic history will be erased, if even the most durable physical records have expiration dates, if consciousness itself is a temporary and fragile archive that is routinely erased, then in what sense does anything have lasting significance? The answer has two parts, and both of them are important. The first part is causal. Every event that happens in the universe has causal consequences that propagate forward in time indefinitely. Not indefinitely in the sense that the specific signal persists forever, but in the sense that every event changes the state of the universe from what it would otherwise have been, and that change propagates causally into the future, influencing future events which influence further future events in a causal chain that extends through all of subsequent time. The supernova that created the iron in your blood changed the chemical composition of the interstellar medium from which the solar system formed. The solar system would have been different without that supernova. The Earth would have been different. The conditions for life's evolution would have been different. You would not exist as you are without the specific supernova that contributed the specific iron in your specific body. The supernova's direct physical record, the light it emitted, the shock wave it produced, has long since dispersed and been forgotten. But its causal consequences are still operating. They produced you. This causal influence extends in principle forever. Every event causes future events, which cause further future events. The causal tree from any event extends to the end of time, even as the specific information about the original event is lost. The universe forgets what happened. It does not escape what happened. The consequences persist, even when the record is gone. This is not a comforting thought in the way that religious notions of eternal record or divine memory are comforting. It does not say that anyone is watching or that anything is preserved in a meaningful sense. But it says something real and something true. What happens matters because it causes what happens next. The causal chain from any event extends into the future of the universe, affecting what that future is like, even when every specific record of the original event is gone. The second part of the answer is about the nature of value itself. The universe's forgetting is a feature of time asymmetry and thermodynamics. It is a physical process. It does not evaluate or judge the events it forgets. It does not treat important events differently from trivial ones. A proton decay event and the first performance of a symphony are equally forgotten by the universe on the relevant time scale. The universe does not know the difference. The universe does not have preferences, but we do. We are the universe's most sophisticated information processors, the systems that experience the passing of time and evaluate events in terms of their significance for conscious beings. The value of experiences and events is not assessed by the universe. It is assessed by the conscious beings who participate in and are affected by those events. The universe's forgetting does not diminish the value of a conscious experience for the being who had it. The full richness of an experience, its meaning, its beauty, its emotional weight, is present at the moment of the experience, regardless of what happens to the physical record of that experience afterward. The sunset is not less beautiful because the photons reflecting from the clouds will eventually be redshifted to invisibility. A moment of genuine understanding is not less profound because the neural configuration that held it will eventually be erased. The value is in the moment. The forgetting is later. And the moments are real. They happened. The universe's physical forgetting does not reach back in time to unmake them. The past is the one thing the universe cannot change, even as it erases the records of the past. What happened, happened. The fact that no physical record of it survives does not mean it did not happen. It means the universe has moved on. The seventh discovery. Before the forgetting is complete, there is an extraordinary archive. Here is something that tends to get lost in the contemplation of cosmic forgetting. The universe right now, at this moment, contains an extraordinary record of its own history. The most detailed and comprehensive archive of past events that the universe has ever possessed. The archive is distributed. It is encoded in thousands of different physical forms. It is impermanent and partially degraded and becoming more degraded with every passing moment. But it is real. And its existence at this moment, in this era, is not guaranteed to have happened and is not guaranteed to persist. We live in the era of maximum information richness. Not because human beings have created a vast amount of stored information, though we have. Because the universe itself at this stage of its evolution encodes information about its past in an extraordinary variety of forms that are still accessible. The cosmic microwave background encodes the state of the universe at 380,000 years after the Big Bang. It is a photograph of the universe in its infancy, still visible in every direction if you have the right instrument. The James Webb Space Telescope, currently imaging galaxies formed when the universe was only a few 100 million years old, is reading from an archive that will eventually be closed. Those ancient photons, having traveled for 13 billion years, will not travel forever. They will be redshifted to lower and lower energies and eventually be indistinguishable from the noise of the expanding universe. The fossil record on Earth encodes information about the evolution of life over the past 500 million years. It is an imperfect and incomplete record, but it is a real one. The specific bones and shells and impressions in rock encode the specific shapes of specific organisms that lived at specific times in specific places. That information is degrading constantly through geological processes. It will be completely gone within geological timescales of millions to hundreds of millions of years. But right now it exists. Right now it can be read. The stars encode information about the chemical history of the galaxy. The specific elemental abundances in the photospheres of stars formed at different times encode the chemical enrichment history of the interstellar medium through which those stars formed. The field of galactic archaeology, using this information to reconstruct the history of star formation and chemical evolution in the Milky Way, is only possible because the archive still exists. The stars are still burning. Their chemical signatures are still readable. The distribution of galaxies across the sky encodes the acoustic oscillation pattern of the early universe. The fossil sound waves from the Big Bang that were imprinted on the distribution of matter and can still be detected in the three-dimensional map of galaxy positions. This is the baryon acoustic oscillation signal, and it gives cosmologists a standard ruler for measuring cosmic distances and the history of cosmic expansion. It is still readable because the galaxies are still there and their distributions still reflect the primordial pattern. Eventually, as galaxies cross the cosmic horizon and the observable universe shrinks, this signal will be destroyed beyond reconstruction. We are living in the brief era when the archive is open, when the records of the universe's history are not yet lost, when a species that evolved on a small planet around an ordinary star can look out at the cosmos and read, in the light of distant galaxies and the microwave background and the chemical composition of ancient stars, and the fossil record of life's evolution, and the gravitational wave signals from cosmic mergers, a history of 13.8 billion years. This era is not permanent. The archive is closing. Every passing year, more information is lost to horizon crossing, to stellar death, to geological recycling, to the simple biological mortality of the minds that store it. The universe is forgetting while we watch, but it has not forgotten yet. The New Horizons spacecraft, which flew past Pluto in 2015, carries aboard it something that will outlast almost everything on Earth. A small piece of Clyde Tombaugh's ashes, the astronomer who discovered Pluto in 1930 and who died in 1997 before he could see the flyby he had dreamed of. The spacecraft is now beyond 45 astronomical units from the Sun, heading outward into the Kuiper Belt. When the Sun becomes a red giant in about 5 billion years, New Horizons will be in interstellar space. It will carry Clyde Tombaugh's atoms through the death of the solar system and out into the galaxy beyond. Some of those atoms may survive as part of the spacecraft for trillions of years, until the spacecraft eventually encounters something that destroys it. A collision, a stellar encounter, eventual proton decay. The atoms themselves will disperse. The specific configuration that was Clyde Tombaugh, the neural architecture that stored his memories and knowledge and passion for astronomy, was erased in 1997 when his brain ceased to function. The atoms of his ashes carry no information about who he was. They are just atoms, now performing a different role in the universe's ongoing story. But Tombaugh happened. The discovery of Pluto happened. The 62 years during which Pluto was believed to be alone beyond Neptune happened. The 1992 discovery of the Kuiper Belt that revised that understanding happened. The 9-year journey of New Horizons and its 2015 flyby happened. All of it is part of the causal history of the universe, affecting what came after, even as the specific records are gradually lost. The universe will forget Clyde Tombaugh. It will forget Pluto. It will forget New Horizons. It will forget every astronomer who ever looked up at the night sky and wondered what was out there. On the timescale of proton decay, all of it is equally forgotten. But for a brief, cosmologically negligible span of time, these things were real, and they mattered to the conscious beings who participated in them. And the mattering was not diminished by its temporariness. If anything, The temporariness makes it more remarkable. That a universe destined to forget everything should nonetheless produce, at this specific moment in its history, beings capable of discovering Pluto and understanding their own cosmic insignificance and choosing to send a spacecraft to visit the world they discovered anyway. That is extraordinary, not despite the forgetting. Because of it. Let's talk about what happens to information in the very last moments, before the universe's forgetting is complete. After the last black hole evaporates, at approximately cosmic decade 100, the universe contains an extraordinarily dilute sea of particles. Electrons and positrons separated by enormous distances in an exponentially expanding universe. Photons at wavelength so long they carry almost no energy per quantum. Neutrinos and antineutrinos essentially never interacting with anything in a universe so empty and cold. In this final phase, the universe's information content is not zero. It is encoded in the correlations between these particles in their specific quantum states in the precise way that the quantum information from all the black hole evaporations is distributed among the remaining radiation field. But accessing this information would require gathering particles from enormous volumes of space and performing quantum measurements of exquisite precision. The energy required to do this, to collect enough particles across enough volume to reconstruct any meaningful information about the universe's history, exceeds any energy available in the universe. The universe has no mechanism to perform this gathering. No concentration of energy exists. No gradient exists to drive any process. The second law of thermodynamics has won. Entropy is at its maximum, and no physical process can extract the information from the noise it is buried in. This is the final state of the universe's forgetting. Not a moment of deletion, not a specific event at which information is destroyed, but a gradual approach to a state in which no physical system has the resources to access any information about the past. The universe's memory does not switch off. It fades, like an image slowly dissolving in a developing tray filled with the wrong chemical, until the image is indistinguishable from the blank background. From this state, the universe could in principle recover some information if it had the resources. But it doesn't have the resources. It will never have the resource. The approach to maximum entropy is a one-way process. The arrow of time that pointed from the Big Bang's low entropy toward this maximum entropy state is the same arrow that prevents the entropy from decreasing. The universe cannot reverse its forgetting. The forgetting is thermodynamically irreversible, and so the universe sits in its final state at maximum entropy, containing within its quantum states the entire information content of its 13.8 billion year history, plus whatever time elapsed between the Big Bang and the final state, encoded in correlations so dispersed and at energies so low that no physical process could ever reconstruct them. The information exists in principle. The universe has forgotten in practice. The distinction matters. It means that in the deepest possible sense, what happened was real. The universe's final amnesia does not retroactively erase its history. The events occurred. Their causal consequences propagated. Their information was encoded in physical states that evolved through time. The information is still there, in principle, in the quantum state of the universe. It is just inaccessible. The universe does not forget in the way that a person forgets. actively losing access to something that could in principle be remembered again with the right cue. It forgets the way a sand castle is erased by the tide. The individual grains still exist. The water molecules that washed them are still present, but the configuration that constituted the sand castle is dispersed beyond any practical recovery. Tonight, we explored one of the most profound implications of physics. The universe will eventually forget everything. We found that information is physical, not abstract, that it is stored in the configurations of physical systems, and that those systems have finite storage capacities and finite lifetimes. We found that the accelerating expansion of the universe is itself an information erasure mechanism, carrying events beyond the cosmic horizon and permanently removing them from the observable record. We found that black holes scramble information with extraordinary efficiency, and that their eventual evaporation releases that information in a form so dispersed that no physical process can reassemble it. We found that every physical medium for storing information, from rock to DNA to stars to the cosmic microwave background itself, has an expiration date beyond which the information it carries is lost. We found that consciousness is the universe's most extraordinary and most fragile archive, producing the most detailed records of experience that the universe has ever created, and erasing them routinely on timescales of decades. We found that the universe's forgetting does not diminish the causal significance of what happened before the forgetting, that every event affects the subsequent state of the universe, even when its specific record is gone. And we found that we live in the brief era when the archive is still open, when the records of cosmic history are still accessible, when a species evolved on a small planet can read the history of 13.8 billion years and the light from distant galaxies. 7 discoveries, each one a different aspect of the same profound truth. The universe will forget. And the forgetting is not the end of the story. It is the context within which every moment of existence takes on a specific kind of significance. Not eternal significance, not significance rooted in permanence, but the significance of having happened at all in a universe that produces and erases in equal measure, that creates complexity and dismantles it, that builds archives and then burns them, that generates for a brief cosmological moment beings capable of reading the archive and understanding that it will eventually be closed. We are the universe reading its own records before they are lost. That is not a small thing. In a cosmos that will eventually forget everything, the fact that anything is remembered right now, that the Big Bang's initial conditions can be reconstructed from the CMB, that the evolution of life can be traced through the fossil record, that the chemical history of the galaxy can be read in the atmospheres of old stars, that human experience can be encoded in language and art and music and mathematics and shared across time through physical media. All of it is an extraordinary exception to the universe's general trajectory toward amnesia. We are exceptions, temporary ones, but exceptions. The universe will forget. It will forget the first star. It will forget the emergence of life. It will forget every civilization that has ever existed or will ever exist. It will forget us. But right now, in this moment that physics tells us is cosmologically brief but existentially everything, the universe remembers. Through us, with our libraries and archives and measurements and conversations and memories, The universe is performing the remarkable act of knowing what has happened to it. That act is happening now. Not in the deep past before any memory was possible. Not in the far future when all memory is gone. Now, in this window. In this era of extraordinary information, richness that will not last but is real and is present. Carl Sagan, whose influence we have traced through several of these videos, once described the cosmos as all that is or ever was or ever will be. He said it with a sense of awe appropriate to the scale of what he was describing. But there is another way to hear those words. All that is or ever was or ever will be is, for a brief moment, here, present, accessible, encoded in the physical state of a universe that knows what it is and knows that it will eventually forget. The universe is remembering right now. Not because it intends to, not because it values the memory, but because the specific physical processes of this era, the stars still burning, the photons still arriving, the atoms still arranged in the configurations that store information, have produced the conditions for memory. The window is open, the archive is still accessible, the records of cosmic history are still present in the light of distant galaxies and the chemistry of ancient stars and the fossil impressions in ancient rock and the neural configurations of living minds. The universe will eventually forget everything, but it has not forgotten yet. And in the time that remains before it does, we are here, reading